all, thank you very much for this opportunity to give this talk. I will talk about how my field of research is in Dubrovin-Frobenius manifolds, and flat F-manifold is a weak version of a Frobenius manifold. And one of the strongest points of Frobenius manifolds is how it works as a bridge between a lot of different fields of mathematics and physics. And actually, you can produce these manifolds. Produce these manifolds from different sources, from data from algebraic geometry, integrable systems of PD, as we saw during this week. Also, as integrable system of ODE, theoretical physics, I mean, physical models, topological theory, so on. And now we starting this new correspondence with the statistical manifolds. Well, I will tell you what flat F manifold is, and by the definition itself is already quite close related with statistical manifold. At least has the same similar flavor, but yeah. We start with a smooth or complex manifold. You should have in the tangent point, in the sections of the tangent bundle, a commutative associative algebra with unit, and a torsion-free connection such that this condition holds. You're asked, I mean, the unit of the algebra is a vector field, and you ask to be a covariant constant. Your connection you has to be flat, and also you have to have this connection should have a compatibility condition with the algebra, the structure constants of the algebra. This condition should hold. This is what we call integrability condition. And indeed, that last condition by the commutative of the algebra and that previous condition implies that you can write the structure constants in flat coordinates because you have flat structure in terms of a potential vector field. Okay, the difference between the Frobenius manifold, you have a little bit more structure. You have your connection is a left shift, a connection of some metric that's flat. And then you can write in terms of a potential function, not only a potential vector field. Another extra condition that may appear is that when your flat F manifold has a vector field E such that this property holds, I mean that they are somehow linear and with respect to these flat coordinates, and have this compatibility condition with the algebra, you call this manifold structure homogeneous flat F manifold, and in flat coordinates this vector field has a Euler vector field form. And in a minute, I will give an example and also the connection with statistical manifolds. And okay, now is a simple definition of statistical manifolds. Is a manifold with a metric and a torsion-free connection. That okay, the manifold should be smooth, the metric should be Riemannian, and the torsion-free connection should be flat, and also should have this compatibility condition with the metric. It's again an integrability condition. You can write GIK as a potential function. That's people like to think as psi, and also people call it free energy. Actually, that is in many cases statistical physics interpretation. And also is an example of a Hessian structure. Okay, and when you are in the specific case of family of probability distributions, you have a moduli space of family of probability distributions. In this space, you measure distance by these formulas concretely by 1 and 2. So sorry, by 1, and 1 is as we already saw during this week, the fish information metric. And also for me, it is important to have the American of tensor. And this provides a way to deform the left-shifter connection of the Fisher information metric. There is about equal alpha connection that also has appeared. And it's nice that for alpha equal 1 and minus 1, this deformation is flat. And also this gives you integrable system of, depending on this, the dimension of your manifold, gives this the dimension of the manifold is finite, give you a integrable system of ODE. If it's infinite, integrable system of BDE, the geodesic, the correspondence geodesics. Okay, and as I said, because of exponential families, the distribution has this form. Now for equal 1 and minus 1, you have flat structures, or alpha equal 1 connection, alpha minus 1 connection. Yeah, and in particular, it's nice. Nice that usually to compute the flat coordinates is not easy. You have to solve some kind of differential equation. But now it's a quite easy derivation to see that once you write your exponential family this way, the thetas do exactly give you the flat coordinates of at least alpha 1. And in these flat coordinates, you can write the geometric structure in terms of a potential function phi, sorry. That's it. And the point here, okay, now what I will do, I will use the Arthur reasoning theory to give a new way to deform the left-shifter connection of the Fisher information metric, in the case of hyperboloid models. And this is given, I mean, I have to have a notion of a multiplication, my tangent bundle, and I take a killing vector. I have to choose a killing vector field of the Fisher information metric, and then I take this second term in equation 4. Take the covector of the killing vector field, take the exterior derivative, and contract with this composition of vector field x and y, and use the product. Okay, the good news that before the left-shifter connection of the Fisher information metric, the Fisher information metric is not flat generically, and it's not easy to give you a deformation in such a way that you have a flat connection. But in this way, you give. And not only that, you have construct this structure here, that F-manifold structure. That things that sound silly, but the third condition here, you have an upper index L, and instead here the correspondent cubic tensor has all the index down, ijk, and this makes difference in the statistical model that you would get at the end of the day. Okay, now I will show you a concrete example. Important statistics, that the family of Gaussian distributions. Okay, you have to take, you consider these functions, but have to consider a family of functions parameterized by mu and sigma. And the parameter space is the upper half plane because sigma should be positive, it's the amplitude of a Gaussian. And mu is any generic real number. Okay, does you have a upper half plane? We know that the Fisher information metric of this family is the hyperbolic metric. That's okay. And this, I'm just refreshing you the standard way to compute the flat coordinates of alpha 1 connection, alpha minus 1 connection. It's just put psi in, p of x theta in the form 3 and compute phi. And okay, and I also have the thetas, and these are the change of coordinates that you have to do to take theta 1, theta 2. Apply Legendre transform. These are standard procediments in the manifold. You get the alpha minus 1 connection flat coordinates. Okay, and then you have your free energy 6 by 6. And now I will give the new geometric structure in the space of probability distribution of Gaussians. That's basically I consider this deformation, this new Christoffel symbol given by 5 is just 4 written in coordinates. But I give this new deformation. And I have to choose carefully some suitable coordinates, but that's just a fine transformation that I made of the multiplication, the tangent bundle, to be semi-simple. And the killing vector field that I choose is the mu. It's easy to see that the lead derivative of the mu in G is given 0. And yeah, and by the fact that you have a hyperbolic metric of constant curvature minus 1, you can prove that this Christoffel symbol here is indeed 0, and also that this condition, the third condition, holds true. That gives you an integrability condition. Thus, you can write in flat coordinates in terms of a potential vector field that's given by this. And this gives you another physical model interpretation. Okay, that's it. Just a new geometric structure in the space of hyperboloid models in general, not only in the family of Gaussian distribution, but I like to understand things in a simple example. And okay, what are the consequences of that? One, there is a standard way to derive a second metric. Okay, the problem that this metric is degenerating some hypersurface, but nevertheless, I can construct a new metric in the when do exist a Euler vector field means this is a vector field that is compatible with the previous geometric structure in this way. When this holds, I can always lift the product, the sections of the tangent bundle to a product in the cotangent bundle, multiply covectors there, and then contract this Euler vector field. And this gives me a metric in the cotangent bundle. Yeah, as long I can also, okay, in the space that the metric is not degenerate, I can also go down to use the Fischer-Hall information metric to define a metric in the tangent bundle as well. Okay, and this condition holds true in the family of Gaussian distribution. This is the Euler vector field. And I do not know, but this could be another, could give you some hints in the statistical manifolds approach, because now I can use this broader geometric structure. Actually, there is I had constructed duality between the multiplication, the structure constantCijk with the, I also like to think this Tijk as a multiplication. Yeah? You can lift the index and create a multiplication table in the tangent bundle, and indeed in some cases this gives you a Jordan algebra. But my case is give me a associative algebra. This by itself is interesting because kind of a duality between those kind of algebras. And yeah, thus I have a new metric and a new way to measure things. And this metric has the name that is motivations in singularity theory. Singularity theory is one source of flat F-manifolds, the Brovin-Frobenius manifolds. And in singularity theory, okay, you study singularities, and this intersection form is quite sensitive to find singularities. the study of bifurcation diagrams and caustics and so on. Therefore, yeah, I hope that there is some application in statistical manifold once you consider the phenomenon of Gaussian distributions, for instance. Okay, now I some further developments in integrable systems of ODEs and PDEs. First, I can deform the flat connection again by the multiplication. And the good news is that now this deformation is flat for NZ. And this gives me a family of integrable systems of Euler-Arnold type. And this would be also nice for the studies of integrable systems in this family of probability distribution. Somehow those integrable systems are telling you how the geometric structure of this statistical manifold is varying point by point. Also, this has some, I think, would have some nice mathematical applications and might also application in data. And also that there is these are somehow a difficult, this would be a standard by itself, but there is a way to produce an integrable system of PDE, given a flat F-manifold or Dubrovin-Frobenius manifold, by using a mix of Dubrovin-Novikov approach and Dubrovin-Jung approach. But basically, a Frobenius manifold is usually a finite dimensional manifold. You have to consider the loop space of this manifold, I mean space of maps from S1 to M. And then there is a way to lift the flat structure in this manifold M to a Poisson structure in the space of maps from S1 to M. And actually the flat sections here give exactly the Hamiltonians of this integrable system that you derive upstairs. And in this way, you can, at least in the case of the Dubrovin-Frobenius manifold, when let's say when the Fischer-Hall information metric is already flat, is already a left-shifter connection of some metric. You have like you can describe KDV, Toda, non-linear Schrödinger. Then yeah, and as long as there already exists the word of statistical manifold, infinite dimensional statistical manifold, you as we saw, you take the Fischer-Hall information, take the Gedex equation, and have equations of hydrodynamic type as well. It might have some nice relations. And I stop here. Thank you very much.